Mr. Sutton here, bringing you this AB Calculus 2-4 lesson on algebraic limits. In this one, we're exploring piecewise functions and the squeeze theorem. So specifically, our objectives for this, we're going to be finding limits of piecewise functions, especially at those border values. We'll also be delving into absolute value functions, which, what's the relationship between those and piecewise? That will be revealed. And finally, at the end, we will tackle the squeeze theorem.
To start us off, I'm going to begin by defining piecewise functions. So this is just a function that's made of smaller functions, which I like to call rules, and each of these rules has its own domain, or x values where it works. We're going to start with a visual of piecewise functions before we try the purely algebraic end. So here's a picture of a piecewise function. We've got 1, 2, 3 different rules going on here at least. One is a line, one's a parabola, and one's another line. Now you'll notice that there are certain x values where one rule ends and the other begins. I'm going to be referring to these as border values in this lesson. These are x values where one rule ends, the other begins. With this in mind, pause the video and using the graph that I just gave you here, see if you can find f of a and limit as x approaches a for each of the 5 a values, x values, in this table. All right, let's see how that worked out. So for f of -3, that's the function value at -3 here. We just look it up on the graph. It's -2. The limit at -3 from the left and the right, and therefore two-sided, is also going to be -2. Moving on to the border value of x equals -2, our function value there is this solid dot, which is at 0 for the y value. But the left and the right side limits don't match up there, so dne is what we're writing for the limit at that border value. Moving on to the non-border value of 1, the function value is 1, the left and the right and the two-sided limit are also 1, so those match up. Moving on to our next border value of 2, we see that our function value there is 4, and then the left and the right sides, they're coming at different angles, but they end up in the same place. They still end up having a value of 4. And then finally, the non-border value of 3, we have a y value there of 4, so that's f of 3, and the limit at 3 is also going to be 4 as you look at it from the left and the right side. So just kind of looking at this table and see if we could strategize for when we don't have a picture to work with. It appears that at our non-border values, -3, 1, and 3, the function value and the limit were the same. So if you had an algebraic piecewise function to work with and you just plug in a non-border value, you know whatever you get back is also going to be the limit. Now what about these border values? Well, we saw at this border value, the function value and limit were not the same, whereas at this one they were. So just moving ahead, we know that at border values, the function value and limit can be different. So when we're doing border values, we're going to have to use a different strategy. At this point, we're going to take a look at the algebraic end of piecewise limits. Here's a piecewise function that should actually be kind of familiar to you because we just saw the graph of this thing in the warm-up. The way these are set up, on the left side here, you have all the different function rules, and on the right side, you have all the domains where each individual rule actually works. For example, this x squared only works, is only graphed between -2 and 2 for x values. So we're trying to find the limit of this thing at 1, -3, and 3 for this particular example problem. Now, why do you think I picked those particular x values? If you take a look at the intervals for my piecewise function, you'll notice that 1, -3, and 3, none of them are border values. They're all squarely inside one interval or another. So to handle non-border values, since we saw that the function value and the limit are exactly the same, for 1 and 2-sided limits, both of them at non-border values, we're just going to plug the x value that we're approaching into the function. So we'll do the first one together. This one, since this is a non-border value, since 1 is not any of these border values, we're really just doing f of 1 here, and we're going to accept whatever result that gives us. Now, how do I actually plug 1 into this piecewise function? To do this, we're just going to use the rule whose interval contains the input. So we're inputting 1 for the x value, so we're just going to look up the rule where 1 falls. That would be this middle rule right here. 1 falls between -2 and 2. So we're just going to use this x squared rule when we're evaluating f of 1. So x squared really means 1 squared in this situation, which means that our limit and our function value there is just 1. Pause the video and see if you can do these other two examples. Alright, so for this one, this is a non-border value. We're really just doing f of negative 3. Negative 3 is in this first interval. Negative 3 is less than negative 2. So we're just going to be plugging negative 3 into the 2x plus 4 function. So 2 times negative 3 plus 4. That's negative 6 plus 4, which comes out to negative 2. And then finally, this last one, 3, not a border value. So we're just plugging 3 into the piecewise function. 3 happens to fall in this last interval. It's bigger than 2. So whatever you plug into this last interval, you're just going to get back the value 4. For this next example, we're trying to find the limit as x approaches negative 2 for the same piecewise function we just used. Now for this one, you might have noticed that negative 2 is a border value. It's the end of one rule and the beginning of another. If we were just doing f of negative 2, then we would just use this first rule because it says x is less than or equal to negative 2. But we're not finding a function value. We saw in our warm-up that function values and limit values can be different at these border values in piecewise functions. And again, let me just go back and show you the picture. Function value and the limit didn't even exist at that particular time. So we need to be really careful with these border values. We have a special process for two-sided limits at border values. It's really the same process we've always been using, but we're going to do it algebraically. It's just the whole find the left and the right limit and compare them idea. So for our first step, we're going to find the left-sided limit. So I'm going to start by writing left and then limit as x approaches negative 2 from the left of f of x. You don't have to write the word left, but I'm just putting it there to be extra clear. So how do we find a left-sided limit now at a border value? Well, these border values, I like to think of them as splitting up these rules into a before and after rule. You have the rule that happens before you get to negative 2, and you have this rule that's happening after you get to negative 2. For the left-sided limit, you're just plugging negative 2 into the before rule. So that would be this rule right here, this first rule. So in this case, this is just going to be 2 times negative 2 plus 4 using this first rule. That's negative 4 plus 4, which means we have a left-sided limit of 0. Now we also need to know the right-sided limit to see if it matches the left-sided. So for the right-sided limit, and I'll write right, and then limit as x approaches negative 2 from the right side. For the right-sided limit, what do you think we have to do? That's right, we have to plug our value into the after rule. So that would be this rule right here. So we would have negative 2 getting plugged into x squared, which we know comes out to 4. Now as our last step here, once we've got the left and right rule, we just compare them. If the left and right limits match, then the two-sided limit is just whatever they happen to agree on. And if they don't match, just like we did graphically, we would say the two-sided limit does not exist. Do our left and right match here? Well, 0 and 4 are not the same number, so we would then say that the two-sided limit as x approaches negative 2 does not exist. We'll do one more example using this piecewise function. Pause the video and try this one on your own. Alright, now hopefully you noticed that 2 is a border value, which means that we have to show the left and the right limits before we make any conclusions. So our left-sided limit using our before rule here, this is going to be 2 plugged into x squared, which is just going to be 4. And for the right-sided limit, as x approaches 2 from the right side, we're using this after rule here, which always just returns a value of 4 no matter what. Since 4 equals 4, since these match up, we can conclude that our two-sided limit is also 4. For the final example in this lesson, you might be wondering what a problem on absolute value is doing in a lesson on piecewise functions. As it happens, absolute value actually is a piecewise function in disguise. To make numbers positive, we either leave them positive if they already are, or if they're negative, we multiply them by negative 1. Different rules for different numbers. So to find the limit for one of these, we're just going to rewrite this in piecewise function form. So to start this process, I'm just going to let all of this absolute value stuff equal f of x, just so I can write f of x instead of rewriting this every time. And then we're going to have this be a piecewise function. Now, a piecewise function, you need a border value to separate one rule from another. The border value in this case is going to be where the absolute value expression, the stuff inside the absolute value here, has a value of 0. So in this case, that would be x equals 2 as a border value, because 2 minus 2 is 0. So we have one rule for the places where x is less than 2. That's going to be the rule where we cover what happens when the stuff inside here has a negative value. And then we have another rule for where x is greater than 2. That'll be the rule where we cover what happens when the stuff inside here is already positive. Next, for the lesser rule where we're trying to turn negative things into positives, we're just going to replace the absolute value with a negative parentheses. Essentially, to simulate the make it positive effect, we're going to take all the stuff inside here and just multiply it by -1. So instead of writing this here, I'm going to write negative parentheses x minus 2 over x minus 2. Now for the other rule, this is a little bit easier because we just want to leave stuff the way it is if it's already positive. For this rule, we're just going to drop the absolute value. So for this one, we'll just write x minus 2 with no absolute value over x minus 2. And at this point, we would try to find the left side limit and the right side limit. But you'll see that if you try to plug in 2, and you might have noticed that there's no x equals 2 case, if you try to plug in 2 here, you're going to end up getting some kind of undefined or indeterminate form. So we can actually go one more step on this problem, and you might notice that this is x minus 2 over itself. Well, that's really just 1 if you cancel those out. And this up here is really just -1. So I'm just going to rewrite this to be -1 and +1 instead of what we originally started with. With this in mind now, go ahead and see if you can finish this problem on your own. All right, so if we're trying to find the limit as x approaches 2, we need our left side limit, the limit as x approaches 2 from the left side. That's just this first rule right here. If you plug 2 into this rule, quote unquote, you're really just returning -1 no matter what. So that is our left side limit. For the right side limit, we're using this rule, which automatically returns 1. So since these do not match up, we would say that there is no limit, two-sided limit, as x approaches 2 for this problem.
Our last topic for this lesson is going to be something called the squeeze theorem, which is a theorem for evaluating certain types of limits. This might also be called the sandwich or the pinch theorem, depending on the textbook or teacher you are dealing with. Here's the idea. Let's say that we have 3 functions, h, g, and f. And these functions we are guaranteed, based on this visual here, just to give you an example of what this could look like, we're guaranteed that, h is less than g is less than f. Basically, g is between or equal to f and h at all x values that are near a certain a value, except possibly at the a value. It doesn't actually have to be true exactly there, but close to there. So if we're given this, and we are further given that the limit as x approaches a of the f function and the limit as x approaches a of the h function, if we're guaranteed that those limits are approaching the same number, we'll call that number L, then we can conclude from this that the limit as x approaches a of the g function must also be L. So basically, if I have these 2 functions that g is guaranteed to be between or equal to over some interval, and at a certain spot those 2 functions have the same limit, then that squeezes the limit of g to fall in line with whatever limit those 2 other functions have. So now that we've seen the squeeze theorem in theory, how do we actually use it in practice? So here's a typical squeeze theorem sort of problem. Let's define g and h as sine of pi over 2x plus 4, and h will be this polynomial with some fractional coefficients here. And then f is some function that is between g and h, satisfies g less than or equal to f, g less than or equal to h, on some interval from -1 to 2. Based on this, they want to know the limit as x approaches 1 of f of x. So first off, how do we know that we need squeeze theorem here? Well, this business about f being between g and h for these x values that are pretty close to the x value they want your limit at, that's a good tip-off that we want squeeze theorem. So how do we use it? Well, we basically just need to figure out the limits of our bounding functions g and h at x equals 1, And then, if those are the same, that'll match the limit of f. And if they're different, then we won't be able to determine the actual limit. So in general, we're going to find and compare the limits of the bounding functions. Pause the video and give that a shot. All right, let's do the limit as x approaches 1 of g first off here. So basically plugging 1 into this g function, we have sine of pi over 2 times 1 plus 4. Don't forget about the plus 4 there. So this is sine of pi over 2, which is 1. 1 plus 4 gives us 5. So that's our first limit. Let's find the limit of h now. So the limit of h at 1, we're plugging 1 into this h function here. And in both cases, we can just plug in because sine is continuous and h is also a continuous function. These are non-piecewise functions at the very least. So plugging all of that in, this is going to be, let's see here, this is negative 1/4 plus 3/4, so that's going to be 2/4 or 1/2. And then we have 1/2 plus 9/2, which is 10/2, which comes out to 5. Since these two limits match, that means that the f limit is going to be whatever these two limits were. So the limit as x approaches 1 of f is also going to be 5. And that's going to give us answer choice C. This next problem is another variation on these squeeze theorem type problems. So this time around we've got three functions, f, g, and h, that are defined here. And it turns out the definitions don't end up mattering, but feel free to take a look at these crazy things. And they're giving us three inequalities in these Roman numerals here. And they're telling us that all these inequalities are true for x not equal to 0. And then they're asking which inequality can be used with the squeeze theorem to find the limit of the function involved as x approaches 0. So we don't have like f, g, and h on the same graph anymore. These aren't three functions that are squeezing each other. Instead, each of these is its own sort of middle of the sandwich in three different squeeze theorem type problems. And we just have to figure out for each of these situations if squeeze theorem would actually help us out. Now remember, squeeze theorem is all about things being in a certain order, which they're saying the inequalities are true, so that much is true, but also you need to have your limits matching. So with that in mind, pause the video and see if you can figure this one out. All right, so for each of these, we're going to go through and just take the limits of the two bounding functions around the original function and see if those limits match. So first off, we have the limit of 1/3 1 minus x squared. And we're asking if that matches the limit as x approaches 0 of 1/2. So let's see here. If we plug 0 into this first limit, that's going to be 1 minus 0 squared, which is just 1. And that's 1 times 1/3 is 1/3. So we have 1/3 over here on the left. On the right side, the limit of 1/2 is always just going to be 1/2. 1/3 and 1/2 do not equal each other. Therefore, the squeeze theorem could not be used on Roman numeral 1 here to figure out the limit of f at 0. I mean, we could tell using sort of a sloppy squeeze theorem that the value of that limit of f is between 1/3 and 1/2, but we couldn't say specifically what it is. Moving on to the next case, if we take the limit of negative x squared and x squared at 0, and we ask if those are the same, well, on the left here we've got negative 0 squared, which is 0. On the right, 0 squared is also 0. Those limits match, so that means that g is going to be whatever limit those both equal. G is actually going to have a limit of 0 as well. In general, yes, the squeeze theorem lets us tell what the limit of g is in that situation. And now for our last case, h taking the limit of our negative 1 over absolute value of x and 1 over absolute value of x in both of those cases. So as x approaches 0 here, this gets infinitely negative on the left side and infinitely positive on the right side. Negative infinity and infinity don't equal each other, and in fact, if you had the same infinity on each side, it also wouldn't be okay because you need to have a constant on each side, a constant limit that these things are approaching. So whichever infinity you end up getting, this is going to be another no. So it turns out only 2 is true, so B, 2 only. So that's it for this one. So glad we were able to squeeze in this theorem at the last minute. Till next time, Mr. Sutton signing off.